Norman, you got the colours slightly wrong for SSBSE. You didn't quite match it to the red of NC State. You know, so you'll have to work better on that next time. So we want you to run the whole conference next year again, and this time get the colours right. Oh crap! Did you experiment with moving the screen back so that you can hear?
To change the the configuration of your laptop, because the screen is good, but just the configuration of the laptop should be changed.
This will normally go to the side.
Yes, just to change the size of the screen. Oh. Well, can you help him with yeah, he want to make it maybe bigger. So.
If anything, we should move the screen back. Let me try the scale.
Yeah, now, yes. Yes, perfect.
Go wider.
Optimize for retainer. Go to optimize.
No, the last one.
I don't need it. I'm just. We find the transfer.
So basically, you're here and then you're leading.
No.
Today is Columbus. Oh, tomorrow.
Okay, morning everyone. I'm your session chair for today's morning first technical session. But before we dive into wonderful research, I have important announced the result from the yesterday's steering committee election.
All right, good morning, everyone. So first of all, thanks to all the people who accepted their nominations and were prepared to serve on the steering committee. We counted the ballots 3 times, and if you want to double check, we've still got them. And congratulations to the new members of the steering committee, Gregory Gay, Mariana, and Mohammed. And there will be, for the new members of the steering committee, there will be a meeting at 12:30 today. Mariana knows the location, I don't.
Yes, it will be on the top floor, so we have a room reserved for that. Yeah.
Okay, thank you very much.
And our first speaker for the session is Tim Menzies, who is so great that he just accidentally finds before talking about this accident, look at last night's accidents. I drove home through war-torn Raleigh. Black is the ace of spades. The only lights were the blue lights of the cops. I was driving underneath trees and falling across the road. I tell you, if you ever get taken to the pub by Claire, stay there. Don't leave the pub. Okay, so this is an accidental exploration of alternatives. My co-authors are only 50% here. Lynn McNair, I have no idea where John Finn is. I'm trying to click. No. No? Okay, does anyone know what that is? Anyone know that? Anyone knows why you should thank this slide? You know what that is? This is This is Fleming's penicillin slide. See that mold there? This is bacteria. See the lack of mold here? Lack of bacteria here? That's penicillin, first cited. It was found by accident. He came home after a holiday and was cleaning up and found penicillin. Turns out lots of things are found by accident. LSD, Velcro, Viagra, dynamite. The American Indians might complain of this claim, but the Spaniards did find America by accident. So lots of things have been found by accident, including an alternative to evolutionary programming that we call SWAY, the sampling way. Now, SWAY was found as follows. We had a paper at TSE 2015 on something called Gale. Gale was written in Java. Zhang Feng was, this is why he's absent. Zhang Feng was porting this to Java and he broke the mutator. And the broken version of Gale that didn't do mutation, which had no impact going after generation 0, worked as well as Gale. So, an evolutionary program that didn't use generations 2, 3, 4, 5, 6 worked as well as otherwise. And that's interesting because Joe Kroll did extensive evaluation of Gale in his thesis. It's a pretty good evolution, a pretty good optimizer. So what we seem to have is evidence that something on the right, something on the left. Something on the left is what we do a lot around here. We select, crossover, mutate. And something on the right is just over-generate lots of examples. A good one. And what I'm going to argue is that the real power of evolution, it was just nature's way of exploring lots of options. Live in different cost-benefit spaces. Biological systems, their only way of exploring lots of options was that thing called evolution. There might be another way to explore lots of options. And we'll talk about that. So that was my motivation. This Gale algorithm, I'll just give you a quick run through on that. So Gale, it was me putting a data miner inside an optimizer. The idea was if we can learn the shape of the decisions, we can build mutators that move things en masse rather than one at a time. And so what Gale did is it built new generations by, first it built an approximation to the current generation. It did a recursive by clustering of the space. It would find 2 distant points and then only evaluate those 2 distant points. And if this point was better than this point with domination, continuous domination, you have an idea that this half of the data is better than this half. And by doing this, by the way, this is actually a analog to doing PCA, finding greater theory. And so if we found this one better than this one, we would, if there was enough in the middle here, we would ignore this half and recurse on this half. So if we found the blue and the red, and we found those examples here that was better than there, we would ignore the red and just reverse on the blue, and thereby ignoring the red from then on. Now, if in this thing we weren't enough here, and if this was a leaf class, say the yellow fellow over here, if we knew that this was better than that, we would push everyone that way at one go. So it was a directed mutate. We learned the shape of the data, and we pushed things uphill in the data. And the point about this process is this only takes log n evaluations of the candidates, and it doesn't run too many generations, so it ran pretty quickly. Too simple, it won't work. Well, it turns out that what we're doing with a fast and loss of PCA, that it's kind of a heuristic spectral learner without all the Farsians and the second eigenvector. Now, we apply this to very big NASA models. This is a model, a requirements model of pilots deciding what to do in a cockpit. And if your pilot's flying your plane, what you want to not happen is them to forget to do things, to be interrupted, to want their interruption time to minimize. You don't want the task delayed, it's the pilot flying your plane. On the x-axis here, 100% is what was in population 0, 50 is half. So if you get down to here, you've reduced this problem by half. The x-axis is number of evaluations. And what you can see is this red line achieves the same reductions as the blue and the green line, but in order of magnitude fewer evaluations. The red scale and the other two in SDM2 and SBSE. We're just as good as more elaborate methods and much faster. So that was a big NASA model. For the usual suspects, we applied Gale. The grey here means that Gale in the middle is no worse than the other fellas, and we're mostly grey. Over here is the number of evaluations for Gale to produce results equivalent to the other fellas. Each one of these squares is 250 evaluations. Here's NSGA2, here's SBA2, and you can barely see Gale's evaluations for coming up with results competitive to NSGA2 and SBA2. So that's Gale. So inside Sway, now it turns out that in the paper, you've got this row, and we did a TSC submission follow-up, and that's the URL. Did you manage to tweet that? Okay, so Vivek is about to tweet this URL and these slides to SSBSE. So if you want to know the follow-up, so for this talk, we're going to have to talk about Sway and Sway B, which is the follow-up to the SSBSE paper. Sway, both of them over-generate a population zero of 10,000 items. Of 10,000 items. Sway works for decisions in continuous. Sway B for binaries. Sway 0 builds its generation 0 by just picking things at random. We have to use a SAT solver for Sway B for reasons I'll get to. We all know the Euclidean distance. I'm going to show you a radial distance function that's interesting. And we both use continuous domination. And the difference of both was the recursive bi-clustering I showed you before. And so the SAT solver, which is pretty common technology right now, I don't really have to explain it too much. But the SAT solver, like, if you have, things expressed in logical frameworks, you can now solve for millions of variables. And we just took one of the standard SAT solvers from the column like SAT4J. The radial, to explain the radial distance function, please consider what happens if you try to solve a binary problem where all the values are 0 and 1. And please consider where those problems live if you float them on a hypercube describing all the decisions. And so if you use a standard Euclidean distance function for that, what you get is the following undesirable shape. You see how all the solutions are living on the corners, on the edge of the shape. Now recall that Gale does this heuristic division of the space. So if I give you this hypercube and start doing slices through it, I'm mostly working in empty space. So Zhang Feng came up with a way of, I'll show you what he did. If I can't explain it too well, this is what he did. He went and he blew the dots off the corners. Now they're floating in the middle of the space. Now we can cut them. So that's the intuition. This is what he actually did. He said, look, our solutions use 1, 2, 3, 4, 5 truths and all that thing. So in this inner radius, I think that only say one thing is true. In the outer radius, everything is true. And we can imagine the graduations in the middle. We pick a random points, and then to space things within a radius, we say, how far are you away from this random point? So at theta equals 0, this point is closest to the random point. And as we come around to here, at theta equals 2 pi, we're furthest away from this random point. So if we split this space in 2, we've found a way to divide things. We're blowing things off the edges now. Okay, continuous domination. This was the core intuition of Zitler's IVEA. So instead of doing binary domination, what you do is you look at the differences between the objectives, their numeric scores, you raise them to an exponential power, and this gives you more information. This is better for exploring many objective problems. Binary domination has no problem with many objectives. Continuous domination is pretty good. So then we did some experiments, 3 case studies. The XMO model, this is a software process model where you have this requirements model. You've got teams with a backlog, a scrum backlog, which tells you what to do next. There are different policies for picking what to do next. The requirements are in a tree. Teams can sit idle if another team hasn't finished their requirements before you. So POM outputs, this is work from Beam and Turner 2003 about idle. Here's some of the descriptions of POM. POM tells you how much work is finished, how much time the teams were idle, and how much it costs to complete. So you want to maximize what you do, minimize idle and cost. There's a whole Jupyter notebook with a working example of POM here. And in software product lines, these two have numeric, real numbers for the decisions. These have the binary, yes, no's, The software product line describes the space of similar systems. And by walking down the street, you generate different valid products for that product line. You can express the tree in a logical format. And you want to use many of these as possible, get as much functionality out to market. And if there's knowledge about, you know, this was harder to build than that one, this one has more defects than that one, and this one was used before, we want to, you know, maximize stuff we've done before, maximize number of features we're delivering to the customer, minimize defects, minimize time to build. And these problems are highly constrained. If you just take the larger product lines and build random true falses, less than 1% of the candidates you generate are valid. So this is why we have to do SAT solving for this fellow over here, because otherwise we'd have no generation zero. And so for the simple models now, the common XMO, recall that these are the ones where we just generate a population zero at random, the decisions for real value, we're working in Euclidean space. There'll be a column showing up for rank, and rank is all the statistical tests round up into one. You know, there's a non-parametric statistical significance test, there's an effect size test, stop not procedure. So the first thing I'll show you is the spread results, and recall that spread means the lower value of spread is better. So here's the median values of spread comparing sway to two other optimizers. The IQR is the 75th minus 25th range. It's a non-parametric full value of variance. And if you want to see it visually, that black dot is the median, and this bar is the IQR. Now in spread, less is better. So the closer these dots are to this side, the better. And what we see is sway, 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 sway. Working is good. Here's the rank produced by these tests here. 2 and 3 are worse ranks than 1. If you go to hypervolume, hypervolume more is better when we're closer to this side. And in one case, arguably, sway screws up. In other cases, statistically, there are some differences between sway, but honestly, if I went to an engineer and said, I'm giving you 100, well, not 105, and I'm doing it, and I'll show you how much faster I'm doing it, 2 orders of magnitude, the engineer will go, sure. So we're okay here on this one. So the really complex models, software product lines, where we have to generate population zero by the SAT solver, because if we go, we won't have anyone in generation zero. We're using binary decisions using that radial distance function. We're comparing 2 state-of-the-art methods from XC15 and ASC13. These are software product lines from the Spot library. These are software product lines configuring Linux kernels. As we go down this list, the problems are getting harder and harder. Again, for these spread results, so sway here is not top, 63 versus 66. I can't think I'll give it to sway for that one. There's one where sway screws up, right here. But what we notice is for the harder ones down the bottom here, sway is always in the top rank. Sway is always in the top rank. And then if you go to hypervolume, sway screws up on the same model here, but you know, sway is top rank, sway is top rank, sway is top rank. Now, so all I've shown you is that sway is arguably equivalent to NHDA2 and SBA2. So why should you care if it's only as good as NHDA2 and SBA2? Well, this is a number of evaluations of NHDA2 and NHDA2 to achieve results competitive to sway. And so here, these, firstly, for the simple things where the decisions are real numbers and the distance space is do, and we generate population zero by random. NHDA2 and SBA2 have to do 30 to 50 times as many evaluations as zero. Now that's not a big deal for these models because they take many seconds to evaluate. But supposing every evaluation meant you have to compile a program, or worse, ask you human being. So over here, recall that the models are more complex as you go along this line. Here sways, other things have to do 200 to 300 times as many more evaluations to achieve competitive results of sway. Oh, sorry, these are the product lines we have to do generations over the SAT solver and working in native space. So, so what are we showing? Well, this community does evolution, and this community, bless your hearts, has never really evaluated the core premise that evolution is the best way to support competency. clearly the optimization methods that Mark Carman surveyed in 2002 weren't good for non-linear, non-current problems. So moving away from standard optimizers was a good move, engaging both most of the power in the results. But have you considered what you moved to? Perhaps there is a better way that does things much, much faster. Now, what I will say is probably better than working in 20 supervised dimensions in raw data. Now, to say this is hardly a new result, but I think it is a new result for you folks. If we look at the history of intrinsic dimensionality, dating back to PCA in 1901, and all the work since has basically said the same thing. You know, don't work in raw data space. Synthesize a more interesting space where moving around is much faster. You can ignore the crap. Well, it's easier. And so the next option, so you know, is sway actually swayed? Or is it a subroutine put to any other optimizer? Like, what happens if we build generation 0 with sway and give the NFGA3? Youngfen's doing that today. He'll give you the results of that by 5 years today, right? Thanks. Hey, not for POM or XMO because they're so simple with sealing effects. We have to, perhaps the simpler the product line, not the other one. Okay, so 5 PM. Thanks very much. Good. Okay, there's all these decisions we made in sway. You know that 100 examples is not enough and 10,000 is good. More importantly, how do we configure sway? We know that sometimes sway didn't work. There were some examples for sway, not many. Sometimes sway, because it's possible to pick a model and say this one really needs evolutionary methods, and this one needs sway. Now, I've got to say, given that sway is so fast, my test to whether sway is any good is to run sway, and then see what you get. Okay, now Vivek's got some interesting ideas. He's talking about audit. Vivek, okay. So Vivek says, how can we audit these conclusions of units? You have hundreds of thousands of solutions in your favorite frontier. Vivek's got hypersampling methods for saying this is all you need to talk about. So it was an SQL with 3.9 million options, and you need to ask people, what was the last number, 65? 64 out of 3.9 million, and he can then tell you how long that was in effect running compiler. So if you have explanation problems for Vivek, Jiangfen when he broke Gale and gave us sway, and then he refixed it with the radial stuff and everything we've seen here. And so he needs case studies. So if you want someone to try this on your stuff, I give you a grad student free, just as long as he's on the author list somewhere. So here's my favorite mouse in the whole world. This mouse is considering making a mistake. He's doing it in the appropriate way. He or she is doing it in the appropriate way. He's preparing for. Okay. Now, if we're not making enough mistakes, not taking up risks, so what does this community have to do to encourage our people to make mistakes? Well, Justina, congratulations. Welcome to working with Tim. I want to offer you 3 prizes for SSB17. I stress these are non-official. These are completely funded by me. But the best buzz prize for the boldest idea. Some of you may not know, but Edward Aldrin, who landed Apollo 11, he flew his PhD to the moon. He was the guy that did the maths for the rendezvous that enabled all the Apollo landings. So how many of you have got the same? How many of you have got a buzz? How bold are you? That's a prize I'll offer SSB17. Also, I offer you the biggest banana prize for the most awesome mistake. So negative results. I hereby declare that SSB17 is negative result friendly. If you have a problem publishing negative results, talk to me and Justina and we'll do what we can for you. And also I have a private bet with Justina, which I'm just telling her about right now, that neither of these awards will be awarded because frankly, I don't think you're brave enough. I don't think you're bold enough. I dare you to prove me wrong. I dare you to make me have to give her $50 for SSB17 because these prizes have been awarded. Okay, so your questions or comments? About 10 minutes. Oh, wow. Okay. Yes, what's your question? Well, why wasn't this stuff discovered before? Why wasn't this stuff? This is a question one of the reviewers had. Okay. And frankly, because we are software engineers, but we've forgotten that the tools we're using are software. Tools like Evo Suite talk about massive collections of everything else except the optimizer. As software engineers, we should be the ones examining all our tools, including core inference algorithms, and we should be the ones refactoring them and trying to improve them. It's very strange to me that most members of this community and of the mining software repositories community use their inference tools as though they're sacred black boxes. When folks, they're just software. And if there's one thing we know how to do, it's how to refactor and improve software. Okay, so pick up your, start stabbing the software and see what happens. Other questions? Yeah.
So if we initialize an SBSE to the same number of random and choose what is that? You are going to get to fill out the output.
Right. Sure. What's the standard population size in the SBSE? 100. So you're now proposing making an SBSE 100 times smaller.
Yeah, but
Worse, sorry. I'm sorry, worse. Because you didn't actually offer the square comparison. So I'm not sure that's the right policy, but what might be more interesting is initialize generation driven in the field to each way.
put aside, I just want to make sure that everything is in bed.
Oh, well, this is heuristic. You saw heuristic. You know, you saw we did. We're not always that good. Sometimes you won't. Sometimes you won't. When you get to this sort of upper level of it, you know from the warm first result that. Oh, anyway, I think you're going to find that. Budget testing, right? That's wrong. Yeah. So the question was, am I channeling theory resulting statistics about if you have a large enough sample? Okay. You did see I was 50 to 30 times faster.
Right, and that's my point, because you just,
Yeah.
you can't, I'm not saying you can, I'm saying that it's something that you may resolve in the field or have been ground
Well, more generally, many things are known. That result is known. All the instrumentality results are known. So why isn't this community more aggressive?
I'm not arguing, I'm
Yes, ma'am.
just, that is what
I think it's very good. Well, probably a little bit louder would be a little bit. What's that, man? What's that you say? Three or four things along the way. Am I just doing random sampling? No. If you look at what I'm doing an analog PCA, but I'm using fastname to generate my okay. So it's not okay. Now characterizing the method, I did on the third last slide. I talked about intrinsic dimensionality. I talked about I really think the intrinsic dimensionality measures. We just say you know stuff like if you increase the radius in the dimensional space, you affect the RVN increases. And you don't usually. You see much less. Like right now, we are not using the 3 dimensions of the space. So down. We're just using 2 dimensions of the space. We could probe realistically the points of the space and say, hey folks, you are not using all 3 dimensions. We can just do a simple thing. I would say that most of the problems with SSBSE, we haven't done the test case generation stuff. We have done configuration stuff like what Steve talked about, and all the standard things, ETLZ, all the usual suspects. We do well on those. So, however you want to characterize the space, I would say it's most of the stuff you folks are doing right now. But there was a point on one of the last slides. There was a point made here, really good at a theoretical result, where this is optimal compared to preferred evolution. But right now, I'm just doing experiments. I totally agree. It's good. If you look at most data miners produce similar results on the data. The thing that determines how data miner works is not, naive Bayes versus mutual sampling and people from both data. It's the data that matters. The reason we went to this topology-based method is we said what we have to do is reason about the shape of the data. Now, you folks are probably aware of the manifold learning schemes. Of the surrogate learners where you build a proto frontier and build different models. A lot of those systems are just far too complicated. But reasoning about the shape of the data would be an interesting. Now we've offered you a heuristic, not just reasoning about it, but also said here's an engineering implementation. And by the way, it's really simple, and by the way, you get very high.
Yeah, just want to, how much the results are dependent to the number of objectives that you're considering? So you try to come with more than 20 objectives and see.
I know we did up to 5. The product line stuff is usually a 5 objective problem. I don't know what happens above 5, but then most folks don't either. Now we have done NSGA3 comparisons. What we find is NSGA3 is dramatically slower, and we're not much worse than NSGA3. And that's for the problems that evaluate like this. So if you start going to more complex problems, you have to compile code or whatever, I really wouldn't recommend NSGA3 right now, based on what we've seen so far. If that was your comment about going.
Yes, this is my comment, because from in practice in general, so one of the questions that always people in the execution computation ask is how much does the execution time matter? Because if the problem is not real-time problem, etc. So having some in terms of compare how much I need to sacrifice, for example, quality or comparing to execution time.
In the TSC paper that Vivek was posted now, TSC submission paper, there's a whole stuff in the beginning, all these quotes about people, all different names, execution time matters, and as a supervisor of students, when you say, hey, go back and do it again, and it takes them 2-3 weeks to fix it. Mark Harmon, 15 years at CPU, software clone detectors, he had to throw thousands of pounds of dollars at CPU funds to get them ready for FSU 15. Okay, so really, you can't tell me execution fund doesn't matter.
No, I'm just saying about how much. Anyway, so yes.
Hello, everyone. Good morning. Good evening. So today we present my students, Vinicius, Eduardo, and the great celebration and support of Claire. The idea of the paper is to improve the crossover operator, actually improve the representation for all of the tests that we might and apply for the domain of problem care. So I will show a little bit about the research-based problem care. This is the ritual. Better? No, nice. Okay, let's start. A little bit about search-based problem care. Production. A very briefly introduction about representation and discussion about preliminary about that. Our proposal, experiments, and conclusion. So the search-based problem repair, some unknowns. Basically, we got a problem, right? Everything, and test suits. Some of them positive test cases, and others negative test cases. Test cases are complex. So after that, we create a kind of variance of the problem. So we try to make the input and create a variance on that, and evaluate each of them to try to find the fix regarding the test through all the tests. So the representation in the literature started with SBSE, syntax tree. Basically, each problem or each variant is a tree, and we create different kind of trees and evaluate each of them, and try to find the best tree that represents the problem. So in this case, this is an example of the problem, of the variant. And of course, it's a high cost manipulation because we have to store the tree, have to manipulate the tree. We have a problem here, and we can't stay. So after that, the people propose a patch representation that's more linear representation that you can express just the edits that you do in the word product. Right? So you just create different paths, and each path you apply for the input, and you try to fix as an output. So you have a bunch of paths. Each solution in the population is a path. Right? That's the baseline now. We are using paths. So each to apply I edit with my code point and the specific fix used in this code point. The combination of many edits create a path solution. Using I edit as a gene, complete the whole edit as a gene. So let me show you an example of the problem. Suppose that we have a fix like that one. So this is the right path. Right? And we are doing the crossover. Parent is like this, and the second parent is like this. So how we can combine the information between both to generate the right back. Between them. So this fit statement is part of the gene. So if you cross over both, you can share this fixed point. Right? So you can touch the target with the canonical, with the current, with the people. So what we can do, maybe we have to leverage, take advantage of more granularity inside the region. Have to increase, actually we have to reduce the granularity. Being lost, this information in the mission, because we can share it. And we need this because the crossover operator is more the exploitation stage of the search, right? So it's good to have more share information, more granularity inside them to share and to make more local search during the project. But again, how can we do that? So we cut the gene. So each gene now is one part of that. Right? So the first part of the gene is about the operator. The second part of the chromosome of the individual is a fold space, and the last part of the individual is a free space. Right? So we divide the representation by the subspace because we have three subspaces right, inside it. So just remember we have parents. And we like to touch this type. Right? So, based on the proposal, we can encode for this representation, like this one, and applying a mask like this one, we can find the type. So, the same parents just change the representation, the granularity of the representation, and we can get the type. Right? We can share this fixed point. So there is three crossover operators. The difference between them is just how to cut the individual to the cut point, basically between cut point, and we apply a memory method I will explain in a bit. So the first operator, crossover operator, is just to cut in the you can cut points, you can put the cut point, the whole individual. So we code, cut, and swap the tails, and have the code after that, and have the everything back. Right? So this is the off. The off one space, we just choose one of the subspace to cut, right? And do swap tails. And then the code again, and generate the back. The unit one space, we use just one subspace and apply math. Generate offsprings, decode, and generate that. So basic idea is just to use more information that population has and avoid to loss them. But this kind of representation, as I said again, generates some kind of loss, right? When we decode, you can lose some information here. So the idea how we can preserve them, so we create a kind of memorization method that can preserve that kind of loss. So we create a pool that we can store the lost information and can use it after with others offspring, after with other populations. Right? So you lost this, you put it in the pool, and the next operator can use it to fix, complete the representation. Right? So the questions about the experiments is how good is it? Right? Compare with baseline, compare with all the presentations. And we test against interclass, PCB, and D. The first paper about the idea, so we tried 43 products to get results. The parameters about the runs, 20 generations, 36, population size, LTV, mutation rate, and some results. Looking for success rate over all runs, we got better results. We outperformed the baselines in all three proposals, all three crossovers proposals. And the best one for this domain, for this program, is the unit one state. So this is a success rate, and success is pass all test fields. And the unit one space is very far better than the original one, and we call the base one. And in this case, memorizations doesn't was very good. Right? So it's close, and sometimes better, like this one, but in general, it's worse than non-memorization, not using memorization. This is about the cost, test number of test suite evaluations. So in this case, we are worse than original ones. We expected that because in fact we are putting more than granularity, right? So we have to search more. We have to do more to find good results. We expected that. In some cases we are better, like this. And this is anything. But in general, we lost the efficiency. And the other result about that is that memorization speed up the proposal. So of course, when you don't lost information, probably you got more results. There is results. So conclusions about that. All new operators are more efficient than the baseline. Unit one space was therefore better than baseline ever, but not for all problems. Actually, 6 to 8. And the new operators are less efficient than baseline. This combination is similar of the baseline, talking about efficiency. Memorization as a tool, because now memorization is a kind of tool. All kinds of individuals in population can use it. So as a tool, do not improve the fitness, but improve the efficiency and preserve some genetic information. If you are looking for balance between effectiveness and efficiency, this kind of solution is the best, right? Because we got good results about efficiency and effectiveness. So contributions about that, we propose a new representations and operators to work with that provide a combination between substates. Provide 6 crossover bonds, and we can translate improvement in effectiveness. Future works, more diverse programs. Local search applies for the new representation because the new representation is gold granularities, so it's good for local search. Apply mutation predictor for that, and try another idea, another kind of representation that we have in the mind. So that's it. Right, just pick from the folder. The folder is completed by the folder that was taken out from like first user file. Actually, you can just lost information, you can complete the information that you want. Could be, could be. But in fact, the idea of the tool is to preserve the good information that was in the population, right? Yeah, so in this case, we don't have information to preserve. So we can just run random or not using anything. Using next. Right, in the control area. Actually, the math is common, like hot point, cold point, but the difference is between the granularity of the information. Right? Because you can use math for different kinds of genes or representation of genes. In this case, the gene is more granularity, it's low granularity. So that's the point why we can improve and leverage the information, genetic information inside of it. How you trust or how you share it is similar. Right? But what you are sharing is different.
Okay, thank you. So I'm going to talk today a little bit about scaling up our fitness function for teacher models. This work is really done by Hamasak Miller, who has now moved to Thailand. He just moved 3 weeks ago, so he can do it with the talk. But this is really his work. So I'm going to start talking a little bit about product lines. Tim already mentioned these today. So today we're really moving towards this product-based view of building software. So we have a set of common features that we can put in every system, and then we have variability, and we can reuse that variability across products and build lots of customized products. So for instance, we have cars here, and we have different horsepower, we have manual, auto, transmission, we have air conditioning and cruise control, and depending which features are in those cars, we can put those together into multiple products. And people have been looking at software product line engineering because it actually after we've built a certain number of products, we start to gain a lot of speed in building products, we have higher quality because we're reusing features, and we're then a push like this. And at the basis of this, as Tim's already shown you, is something called a feature model, and that's really where my focus is today. So let's look at what this feature model is. So we have a feature model for a car, and we kind of two parts to it. This top part just tells us we have a car, and then we have some mandatory features here. So every car has to have a transmission, has some type of horsepower, has an engine, and then we have some other kinds of relationships. So air conditioning and cruise control are optional, you can have cars without those. We might have either auto or manual, so we have an alternative, but we can also have both, so we can have a gas and electric, so we kind of can have an or. And so we have these models, and we have all of these relationships in the models, and they become very hierarchical, and they become easy to read. We can have multiple layers of dependency. Then we also have something called cross-two constraints on these. So for instance, we might have a constraint that says automatic implies that we have air conditioning, or that manual implies we don't have cruise control. Or we might have something more complicated, such as gasoline and electric implies cruise control. And so altogether, both the diagram and the cross-two constraints make up my model. Even cross-two constraints are easy or not easy to see in the model, but you can have some variation where you put them. Okay, so when we have this feature model, it's been used a lot for things that focus helps us abstract. So we can see the entire family from that model. We can ask how many products, we can look at different configurations. We can ask if something is valid. So there are analyzers out there. So one that we're using is a feature analyzer farm, which actually can tell us, ask questions about is something particular configuration valid. We can optimize so things work, looking at ways to optimize in multiple dimensions, constraints on models, and also we can do things like test them. So feature models are really important, and we use them in a lot of situations. Problem is, feature models don't always exist. In fact, quite often they don't move along with the product line. So if we don't have a feature model, we have to either go back to the manual documentation, or we might have some other information. So we might have, for instance, a set of valid products. We might know what the products are that are in that set, or we might actually have source code, and we might be able to gather some set of constraints from that source code to build the feature model. And this is where we're really focusing, is on these two pieces. So there has been a series of work, this is not new, where people have said, we're going to take the products, or we're going to take the constraints, and we're going to reverse engineer a feature model from that, so that we have this nice graphical representation, we have the hierarchy, we have the cost, the constraints, and we're going to build that. So there are a couple of existing frameworks. One is called EFON. This was originally by Lucas Herman, and then we built on that a year or two ago to build something called SPL Repo. And in these, these are frameworks, and what they do is they genetic algorithm. The idea is we come up use a GA and we evolve it, and at the end we have this evolved feature model which should match the original feature model. The thing is, we started working on this, and we started to think about, well, now that we can actually get these products, we know what the feature model is, can we do other things? So can we add other quality objectives? Can we go to multiple objectives? We're not going to do that in this talk, because what happened is we ran into a roadblock. We were trying to do this, and we realized that there were some limits on what we could do with the existing tools. And that's what we're going to talk about today. So let me look at a little bit how we do this reverse engineering and how people have been doing this reverse engineering. So we have to start with the desired set of products, which could have come from some constraints. And then we have our evolved products, which are every iteration of our genetic algorithm. And what we want to do is we want to put them together and say, how well do they match? So we might have, for instance, additional products that are in the evolved one that don't exist in the original. We might be missing some, and then we might have some matched ones in the middle. And of course, what we really want to do is we want to put those together and we want to get a match that looks like this. Problem is that the solution today has been, we're talking about products, we're very product-oriented view, and so what we're really trying to do is think about checking individuals. And so if you think about how large a product line can get on all potential products, not just the constrained products, this is going to be a bottleneck. You have to enumerate products to do this. So let me show you, this is one of the fitness functions we use. This is one of the better fitness functions. In this, you can see what we have here is we have essentially this SFS are our, so we have 18 products in this particular system that we're trying to get. The match products, the additional products, there's some logarithms about the fitness function. But basically, we're looking at the matched minus the additional over what we're trying to match here, and then calculate that this way. There's other actual fitness functions, but if we look here, we can see that if we have an exact solution, we're maximizing what we're calling validity. We actually maximize it at 100, and the next best fitness function, which came out of decom, which we also look at, is minimizing it at 0. So we match, when everything works, we match well. If we look at an example where we match all the products, we get 18, but we have 6 additional, so it's not perfect. We have about 93.4, so we're still maximizing, we're still pretty good. Again, it's min diff, it's minimizing, it's still doing good, but it's really showing and highlighting those additional products. We have another situation where we still have 6 additional products, but we now are missing 12. You can see what happens here is min diff still has that 6, so it's not quite as sensitive, whereas our fitness had gone down this validity. So we're working on this validity function, and this is what we're doing, but again, these are, so they're a little bit better, but they're all based on these products. Okay, so why do we care about this? Well, let me show you some times. This is times in hours, and this is the number of features in a product line. And so you can see that here we're running, and everything's looking great, and we get to about 27 features in our product lines under the current implementations, and everything comes to means we can't actually calculate the products in formal, we can't actually do anything, and so we can't evolve our system. So we sort of hit this point where we could no longer actually do our genetic algorithm because we're trying to enumerate products. But things like Linux, Tim also just mentioned, has more than 10,000 features, potentially 2 to 10,000. We can't possibly do this. Now, they may be very constrained, and that may not be the reality of what we're going to see in the final system, but as we're evolving, we have to let this expand and remove and extract constraints. We need to be able to handle that many times. But there's been some other work, and so there's a group that was looking at extracting constraints from code, and they realized that Linux has only 12,000 constraints. There's 2 to the 10,000 products, but the constraints that describe it are much less. And so they were using constraints in order to be able to calculate how good their extraction was. And so we started to look at that and say, can we use that as well in our future model in evolving systems? So one of the systems we used in the past, mobile media, has 184 possible products, but if you look at the constraints, there's only 32 constraints to describe them. We started to see, could we actually use this and leverage this in our fitness function? Okay, so we thought if we can utilize the constraints, and we could then use that to evolve our products, we might be able to scale more, and so we'd move from a product-based view to a constraint view. That's really what we're trying to do here, and we didn't really know if this would work, so that's kind of the point. So let me give you a little background just on SBSE to give you a flavor of what this genetic algorithm is doing. Then I'll talk about our new fitness function called SAT-FF, and I'll talk about our study and our results. So just to give you a sense of what's happening in this genetic algorithm is we have our feature diagram we saw before, and what we do in our chromosome is we have each gene has a set of children, the parent and the type, which is just some hierarchical relationship, mandatory or XOR mutex, so we just keep that relationship. So for instance, if I come here, you can see, for instance, that transmission just has a hierarchical relationship with car. Gas has a hierarchical relationship with engine. But then we start to see also that here, gas 1 and 2 has an XOR with engine. So we keep these in our chromosomes, how we represent them. The reason we're using this particular framework, SBSE, is because we added some features that weren't product lines that were being lost in some of the other representations. So that's what our first part of our chromosome looks like, but we have to have two parts. Remember I mentioned we have these cross-Q constraints. So we also keep cross-Q constraints, and in order to allow for complex ones, we actually build a tree. And so now we have a type, the feature, the origin, destination, and now we take all of our constraints and put those into a tree. So now we've got two parts to our feature model, to our chromosome. What we then do is that in order to do crossover, we can actually do a structural crossover. So we can take two feature models, and we actually can pick a point, and we can now just structurally cross over. So this is how we're working in this SPL Revo. I'm going to show you the fitness, so now you have some sense of what we're doing. Okay, so as I said, we couldn't get this fitness to work, so we wanted to look at how we could actually build this new fitness function, and we wanted this fitness function to be built on constraints. So let's look at these constraints. So I have on the right here the evolved feature model, and I have on the left the original input feature model. And I know here also we can have source code, because actually one of the nice features, part of our framework is we're being able to, we're actually extracting from the source code. We do some experiments here. Or suppose we don't have a set of products, we don't know what those constraints are, we might pull up the source code. Okay, so here we can take our feature model, and we can look at the constraints that are just underlying that model. So in this case, you can see that we have, for instance, A implies that we have SPL, B implies SPL, B implies SPL, and we have some here for C and D. We have SPL implies C or D, and C implies not D. So that's going to kind of handle all of these things. Now we do have, because B is mandatory, we also have here that SPL implies D. So we have a bidirectional there to make sure that we have that mandatory. Okay, so that's on our left side. And on the right side, it's exactly, there's a few things that have changed. First of all, we've removed this XOR on C and D, but it's actually been moved down now across two constraints. So actually, the underlying constraints still change. Our model has been refactored, but the actual underlying constraints, they don't change. But what we have done here is A has now become mandatory during our evolution. And so now we have a situation where we now have to add one more constraint, that SPL implies A to get that bidirectionality. Okay, so now we've changed that. So we want to be able to see, can we tell how good our model is by looking just at these constraints? Remember before we would have counted products, we would have figured out what's there. So the first thing we want to ask is how many products in the feature model are correct? Well, if we look at just the constraints, here we see that we have the same, so every constraint that is on the left is also on the right, which means that we're as constrained and any products that are there are correct. So that we know that our products that are in the ball products in this new model, because this evolved feature model isn't going to have anything on A is optional because it's not allowed because of that new constraint. So we're actually going to be missing products. So we're going to look at that, and we're going to actually look at that as a recall. We're going to kind of put those two together. So essentially, and then we're going to ask the negation is we're going to use tautology to make sure that we actually can show these things work in all directions. So what we're doing is we now use a left measure where we actually heuristically determine that we want to count recall to count at a higher weight. So we're using data before here that seems to work pretty well, and this is our fitness function. Now, a little careful, this is study. We wanted to know does this even work. So we first asked about the quality of the features generated compared with two of the existing fitness functions. So we have the min diff, which was the original one. That was one that we was doing at 6. It didn't have quite as much variation in validity, and we have validity that was our fitness function. Then we asked how well does it scale to these larger feature models. So we used 101 feature models up to 97 features. So remember before I said we could only go up to 27, so we come up to 97. 92 of them are from or is it SPL? Well, these are from the original work. So it was based on the numbers of features. So you see 9 to 10 is in the small, up to 10 is in the small, up to 20, up to 19 is in the medium, 20 to 26. I mentioned earlier, these are very constrained. But the problem is that when we're actually evolving, we have to allow them to unconstrain. And so in our logs, we see sometimes 1.2 million of these numbers of products. So we have to count a lot higher than we do than the actual value in the real university. Then we added what we call extra large. So these extra large, we took 9 models in the SWOT that had between 40 and 97. And then we went and got a C program, now XML, and we used, and we pulled out the constraints from that, and that had 52. So this is just using the constraints from that system. And as I said, we saw instances up to 100. We take our feature model now, we use these 3 fitness functions, and then we compare it with as we develop. So we encoded SAT using DocuDB. We ran our experiments 10 times. We used the SPL variable framework so we could use those more complicated chromosomes and crossovers. We both really in depth. And then we used the GA17 file paper to make the C program. We use PyCamp and parse to actually do some extraction. And there are artifacts available through the models for you to check that. So we want to look first at the quality of the feature models, and I'll show you different versions of this, but just to quickly show you the raw data. So you can see that the validity and StatFF have our best F measures. So here, large, we're just comparing it against the known work here with the small, mediums, and larges that we have. Here we use the balance F measure with F1. So you can see here that if you look at, so validity is giving us the best results, and that's known from actually from our prior work. We're always getting better results with validity in this framework. But what's interesting is this is StatFF. You can see it looks almost the same. As a matter of fact, in the last one in large, StatFF is a hair higher in its F measure across all the products. But it turns out that we actually did Mann-Whitney. There's actually no difference across any of these. So what we're seeing is StatFF is as good, or you could say that validity is as good as StatFF. Which is exactly what we wanted, because now we have some confidence that this actually works, and we have quality of our feature model. Then we look at scalability. And here we see StatFF, and you can just see these are times in minutes. You can see, things like 11, 147, 800, and you can see here 0.1, 0.2. So we're doing much better. I'll show you the form in a minute. The maximum extra large, we did take about, on average, looks like about 16 hours. So it's still taking a long time, but we're getting results there. So if we look at the same kind of view for scalability, and we're looking at the log time here in minutes, you can see MinDiff was the fastest of the other 2 feature models, and we paired against that. And you can see here we're seeing a big difference with that and SAT. So we're seeing a much reduced time. Now if we look at this on another form, what you can see is on the x-axis are the number of features. So this is 27. This is about where we had a cutoff before. The red so here with just the small, medium, and large, the percent improvement. So 85, we're seeing the difference in time. So we're seeing big differences for validity. And for both of them. And you can see the extra large scales all the way up to 97 features forward. So in summary, we presented a new validity fitness function based just on the constraints called StatFF, which is estimates the difference between the input constraints in all models. It produces accurate feature models, where the measure is high as validity. It's more scalable as an alternative fitness function. Unfortunately, it still isn't scaling as well as we'd like. We haven't really gotten much above 100 features, and so we're looking at some other techniques. So we're looking at using incremental solving, some model counting. There's new model counting idea we use. And we're also taking this, now that we have this scalability, we're looking at multi-objective optimization, because what we really wanted to do is be able to start handling multi-objectives when we refactor our system. And we're also evaluating the quality of our feature models for concrete activities such as testing. Well, I'd be happy to take any questions.
Yeah, I have a question about the parameter setting. So when you did the comparison between used exactly the same parameter setting for the algorithm?
He's asking that I'll repeat it. So.
Yeah, that's my question. I didn't, maybe I'll find it in the paper.
Parameter settings, I said we use the same parameter settings. So if you go back to the original econ paper and then the SPL Revo, I didn't put the table here, but we use the same number of generations, the same type of selection crossover, because we just wanted to compare it with the prior work. So we might not have been as optimal as we could have been, but we just tried to keep it the same as in the prior paper, just to make sure that, and that first one was really just to see if we could get the same results. So we just used all of their parameters. Yeah. Well, no, at least, so I didn't actually write it in, so that was just the way it ended up magically, which on my slide happened to be very non-random. When I do my crossovers, I have other slides, I don't have them here from the original work, which is another paper. We actually have very specific crossover operations, and we crossovers on the tree and the cross constraints separately. So it could, by some very small random chance, turn out that we've got a situation where we happen to just change one thing on the feature model that matched what we changed on the. So that was not like a random change together, it just happened. So this is, we're actually working at, so some of the motivation, as I said, was for this sort of multi-objective, and we're looking at, we actually have some really nice results on something called simplicity, where we're trying to simplify, so instead of just having a feature model as with the correct products, we try to also simplify it. We have some other quality objectives as well, and then we do a multi-objective. But one of the objectives has to be this validity, which is where we ran into the problem with this priceless paper. But yes, we are looking at that, because it makes a difference. If we pull all of our constraints down to class 2 constraints, it's a terrible model to work with. So we're calling it simplicity because we want it to be, we want to push them up. So, you know, we're doing this actually, I should be careful, we're not doing it intelligently in the sense that as we do our mutation and as we do our crossover, we're doing it, but we're evolving it that way. So we could do something better, which is what you're saying, which is to think about it when we're doing it. But sometimes I find that search is better to let the search evolve than for me to try to push it too much intelligently, because I might not make the correct choice. But yeah, that's exactly where we were going when we ran into this roadblock of not being able to get things to scale. Because if we're doing a multi-objective, we still want one of the objectives to be that it's correct. So we still need that validity fitness function no matter what we do. The runtimes matter? Yes, runtimes do matter because we're also running out of memory. So not only because we have to use stat solvers even in the products. The product one is actually asking questions against the stat solver, and that is running out of just memory and time. So yeah, it really doesn't matter. But that is your advisor, so I'll let him tell you.
My question, are you considering a fitness function, maybe some priorities that you're giving to the features, or maybe the degree of importance that you include to the product?
So we could. So as in this next version that we're working on, this multi-objective version, which is there, it's just not out yet. That one, we haven't looked at that particular quality objective. We've looked at a couple of others, but that's one thing we can put in. So we're building a framework where you can actually do a multi-objective and have different kinds of qualities, such as a prioritization, which ones are more important, or which ones, or this idea of simplicity, where we can say other things about the feature model matter more than just the correct products. Because if we're going to basically rebuild the tree anyway, rebuild the feature model, we might as well do it for multiple objectives at one time. So that's so right now we have an industry that we're working on with multi-objective.
Yeah, that's very interesting because they had just conversation with the industrial part, because I like the example that you give from automotive industry, because when they're manufacturing cars, they try to look at the product, and he actually was mentioning that the different level of importance of the features. That's great. Yeah. Yeah, that's good.
That wasn't important to some other quality objectives, but other ones that we thought were important. And we do have an implementation of that.
Great.
Yeah.
Excellent.
This is probably not the features, but are there any cases where you change the model and then
So there are, okay, yeah, so this is not the full talk of the SBSE, because that was another paper. In that paper, he does actually have a way to manipulate the model at the end to make sure that it works, right? So because you could actually create a model which is the constraints are invalid. So he actually, I think, does it. I don't know the exact method, but he does in his crossover. He does check them. It is very easy to get invalid.
that's the first
My whole time now. If your watch was correct. Oh. So I have to say
be exposed. So here's a silly example of a piece of code. It's for loop that creates an array list and then does things with the list. And this L2 here is quite a good example of a deep parameter. When you initialize an array list, you can set how much the array list size should be to start up with. And you can see in this case, this is just inefficient because you only ever add one to this list, so if I initialize it with just a size of 2, one size of 1. The deep power quantization only does things like exposes all the integers in a piece of code. So in this case, you replace all the integers with placeholders, and then you set those placeholders at a higher level that can be optimized by a parameter tuning algorithm. And the idea is you're probably, by tuning a great amount of parameters, get further up the scale. That's a general idea from deep parameter optimization. So what exactly are we optimizing in our case? We created an application that we just call classify images. And classify images is very basic. It reads in an image and tells you whether there's a face in that image or not. So a face, and it returns true, and you got an LDA6, and it returns false. That's very basic. And all this classify images takes in as an argument is a directory. It will search that directory for images and return back human readable lists and image name, true or false. Okay. So inputs image set, and we can easily determine our human function attributes in this. We can measure the execution time, and we can get a classification accuracy because we know beforehand which images have places in them and which do not. And there's also a trade-off between these two. Our classify images application obviously uses OpenCV, and in particular, a class called Cascade Classifier, and in particular that, a method called Cascade. The Cascade Classifier has to be initiated with a hard cascade. All hard cascade tells the Cascade Classifier is what feature is it looking for. So in our case, we use OpenCV's hard cascade interface alternative classifier. That's included in OpenCV because in facial detection is a very common usage of this sort of application. And we profiled our code to see which files are used most often in OpenCV and running our application. And we found, I think, it was above 90% anyway, of the execution time occurs in this cascade detect file and its header. So we decided that we just simply optimize this file. So this is the file we're modifying in our deep parameter optimization. The first thing we have to do with these files is expose the deep parameter. And it's very simple. First thing we do is to expand the search space. We change all instances of plus plus to plus equals 1. This means that our deep parameter optimization can increase or decrease this value, so you can have plus equals 2, for example. It's just a way of expanding the search space from what possibility. Second thing we do is we identify all the integers inside the search space. And that's just done doing a direct script. We replace all these integers with unique identifiers, and then we set them as defined macros in a separate file. So you can see here, you can see with a simple set of scripts, you can toggle these parameters as you wish. And we go back to this file and include the defined file. And at this stage, the code is functionally equivalent. In fact, I think because we use unit processing macros, then I think binary will not be the same thing. So once we've done that, we've exposed all parameters up to level 2. However, there are a lot of integers inside source code. In the case of Cascade Detect, we have 537. And we could start optimizing from here, but my feeling was that this would probably make the algorithm a lot longer than was necessary. And we suspected, and this is backed up by what I'm about to show you, that most of these parameters aren't worth tuning. They either cause the program to crash or don't do much if you change the value by the alignment. So we basically have this filtration step. And the filtration step is sort of in 2 parts. The first part is we get rid of parameters that we think are too sensitive. That is basically you change them by a tiny bit and you throw the program completely off. You make it crash or it can't compile. So for each deep parameter we've exposed, we increment the parameter by 1. We run the program with this altered parameter with the randomly chosen phase image. And let's imagine in this case they crashes. And they serve this rule that replies that, okay, if the program did not compile, crash, or did not produce a parsable output, then we simply leave it. It's too sensitive, it's not worth having in our parameter. And that gets rid of quite a lot. And we do it for the rest of the parameters. And then we have the second position set, which is the opposite. It's basically too insensitive. You vary the parameter by a huge margin, and it doesn't seem to affect the output at all. It could be that this integer is just never used in this particular run. So all we do is we go through the remaining parameters and increment by 50. And then we run the altered parameter from the training set. And then if the program did not compile or run in the same time as the original, this parameter is removed. What I mean by the same time, we run the original application 100 times on the training set and got a 95% confidence interval. So let's imagine in this case 95% confidence interval is 59 to 60 seconds. If it falls on that, we can say, well, there's not been a statistically significant variance when we change this parameter, so we're just going to do it. And again, do the same for the remainder of the parameters. So at this point, I'll give you a brief overview of what we've done. It's quite straightforward. We have a classified images application, which heavily uses this cascade detect. We expose the deep parameters in cascade detect, that's 537. Then we run our filtration set to get rid of all these deep parameters we're not that interested in. We get that down to 51, so it's 10% of its original. And now we're basically ready to start optimization. So we use NSJ2 as implemented in the mode framework. And all this really does, in principle, from a high level, is it alters the deep parameters and then runs the classified images as a fitness function. And hopefully, at the end, what I'll do frontier, we'll get this time accuracy data. The stage will point out that we have a training set that classified images runs each time, so it runs the entirety of the training set for each evaluation. I'll briefly talk about how we get this training set. We get it from 2 data sets available online. One of them is the University of Massachusetts labeled places in the wild. What it means by in the wild, as in it's not like portraits, it's like people going around doing shopping and doing work, so the places are sometimes a little bit off center and things like this, so it's a bit more challenging for a face detection algorithm. And then we also use the Caltech 256 dataset for a data set of no places. This is basically a data set that contains images that are tagged with descriptions of what's in that image. And all we do is we filter out all the images that are tagged as having faces in them with our data set. So for our training set, we get 3,000 images, 50% from each of those data sets. And we'd also create a much larger test set that contains 17,000 images, each from 50% of each. So both of these are 50% faces, 50% non-faces. And we know we've got actually a reference of which of these images have faces and which of them don't. Just for reference, our classify images application, the kind of vanilla version that's not been modified, will achieve a 0.9% in accuracy on the training set and 1.04% in accuracy on the test set. So we run this NSJ2 algorithm on this. We run the NSJ2 algorithm. I'll quickly go through some points that are probably worth noting. We run the NSJ2 algorithm on 100 individuals over 10 generations and give you a kind of wall clock time that I think it's worked out to be around 8 hours or something like this. So it's an overnight thing anyway. It's not days and days and days. To measure the time, we use Unix's time utility. And this was running on Amazon EC2 instance if you like backdating somehow. And we did some things to limit the scope of the search, just to we thought these were sensible moves. We limited the parameters to maximum 64 and minimum 0. And the initial generation exceeded with the original parameters and parameters that were in the neighborhood of the original version. So basically this was the original parameters with usually one parameter with +1 or +2. So what did NSJ2 give us when we ran this? Well, we got this creator frontier, and we were quite happy with this because I think we all have this idea of what a Pareto plan should look like, and sometimes we don't really get it. But this really does look like a textbook Pareto plan. It's nice and curved, it goes down. This blue dot here is the original, which actually in this case isn't Pareto optimal, so that's why I'm highlighting the blue. I just thought I'd include it. Reference. At this stage, we thought, well, this is great, but is it overfitted with the training set? So basically what we did, we all these points you see here, and ran them on the test set. And then we plotted it again on another page. So we think that through. If it's not overfitted, the Pareto function look very similar in shape. It shouldn't alter very much. So if you just keep an eye on this, this is the training set, and this is the test set. Training set, test set, training set, test set. Very similar traits, right? So we're not overfitting. This is a genuine result. There's only two things that have changed when we run and then test set. The first is the original version here is Pareto optimal again, so we re-included it in the Pareto fund. There's two solutions that are included in here. One of them crashed from the test set, so we just removed it. Another one was dominated by others in the population, so we just removed it as well to just want the final Pareto fund. I'm going to briefly talk now. This looks impressive, but I want to talk you through what it means in practice. The original here ran in 191 seconds with a 1.04% accuracy. So like this one here, it's almost half the execution time. So 48% decrease, or 1.8% accuracy. So basically what we can do is half the execution time if we only get set 0.76% percentage points increase in accuracy, which we thought was quite an interesting result and one that potentially many practitioners would be willing to make. We go further down, we can get up to 64%. Down to 76% decrease in execution time, depending on what sort of accuracy you want. And quite pleasingly, I thought this point at the end here is 50. And if you remember, the test set is 50% basis, 50% non-basis. So 50% classification accuracy is basically randomness. It's kind of useless as a base classification algorithm, but it's nice that we've got a scale here that goes from completely useless all the way up to the best possible time. So useless up to only 1.04%. And I like to keep the results on screens, and I'm quite happy to end my talk there. If you don't have any questions. Are there any questions? You can't see. That's what the group of color 537 is. So there's 532 variables. We only have to run 532 runs to filter them out, right? We went to each parameter and added one, and then if it failed, we filtered it out to the next one. So it was actually quite quick. I think a couple of hours to that filtration. Thank you. So you're asking, does this suggest software is fragile? The other papers that I've read in fragile research or random have used very different operators that remove entire lines of code. I think what I'm doing here is the integers, which often are how many times a for loop is iterated and things like this. So maybe there's something in that. It does appear to break enough of it more. I can't give you, I don't have the statistics on hand that how many times it breaks. But yes, it would suggest that if you just toggle random, well, there's two sides to it. Either you toggle a random integer and it breaks the program, or it doesn't do anything. So it's either really insensitive or too sensitive. So we were trying to find a sort of Goldilocks zone where things were sensitive enough.
Additional questions for you? How did you choose them?
Okay, this was actually one of the reviewers pointed this out. So we limited it to 0 to 6 to 64, and the reason for that is when we got down to our set of 51, that was the range. I think the minimum was 0, and the maximum I think was 32, so we thought 64, but it was just an arbitrary place. We just thought that this might limit the search space a bit, and we didn't suspect things going above that would be very useful. But it wasn't based on any sort of popular encouragement. Yeah, I think looking back, I was a bit paranoid that this might run on for too long, so I was quite careful at limiting the search space. But given it running 6 hours and got pretty good results, I think next time we'll be willing to go away that restriction.
Any additional questions for us? I did have one question. Can you briefly comment? Is the process of exposing the deep parameters done by human beings who modifies the code, or is that done automatically?
Exposing deep parameters is automatic. We basically a script. Well, it depends what deep parameters are interesting. We took the easiest deep parameters that are just integers. So we have a regex expression that identified integers and then the first integers used. And then we populate it. And it's all done through a series of scripts. It's all automated.
And then the only final question I have you presented your results to practitioners who use OpenCSV? What did they say?
I wish I did, but I didn't. So, no, I haven't showed this to anyone who actually uses this. We were hoping to acquire a donor and use the software, but there was a problem with them to make them things, so we didn't do that.
Okay. Let's thank our speaker with the final round of applause. And please welcome our second speaker. David is going to be talking to us about regression testing, specifically for the Motifo artifact. Let's welcome him with a round of applause and thank you for the Thank you. So after having a great presentation from models, experts in advanced tuning, giving you exemplary application, I'm going to give you something different. This is going to be a case of moods approaching testing. So I've never done any software testing before. So it's an interesting experiment because from the discipline. So this work is a collaboration between myself at UCL, Queen's University of London, and the University of York, and North London as well. There's an inter-objective regression test minimization from Motifo or Motifo or Motifo, depending on where you're from. It was a collaboration with Andrew Turner. And I have to say that Andrew did the lion's share of the work in this. I've joined both set up some documentation. Unfortunately, Andrew couldn't do this today, so I'm going to tell you and also with John and Joe who worked on analysis. So the idea here was to focus on Motifo, which is one of the software packages for charge. Does everyone know what Motifo is or know what it's not? No, that's 15 minutes. Okay, so I'll explain that. essentially, Mojito is for Java, and it's for building unit tests. And what it allows you to do is render components that are artifacts or environmental conditions that are hard to replicate. For example, filling an exception due to some device problem, or connecting a database, access to a local unit test. It allows you to create more objects. So here's an example which I took from the Mojito website. What you see here is we're mocking up a limitless object. We're saying here, whenever you get a request, or you request an item in the list, here's the requirements. So you don't need to go and operate our list of those and lock it with the spec. And here, you get no because we can do anything in terms of spreading out the data. Another example, which I based on something from the blog, this is where we expect, when we call queries here on the output, we expect to be passed on to our mock object. And the mock object can actually record what's happening in terms of the behavior of the coding on the test here. So then we can verify, we can have an assertion that says, this guy was called during the process of our test. Okay? So you can check that the behavior of the system is as we expect by when we call it by the mock object. So the goals of our work have been introduced twofold. First of all, regression testing optimization has been done a lot before, of course, and our aim here is just to see how well we could do it. As simply we could do it with modern ability. Just by the project, as Greg said yesterday. So it's interesting to see how difficult it would be to optimization. Because we can keep testing loops, it was just interesting to us to see how difficult it would be to get it to work and see what we could learn ourselves about software separation. The second part of it was a curiosity-driven idea, which is, if you think about Mojito, right, it's all about testing. It's written by people who are experts in software testing. So their unit tests are going to be pretty good. You expect these guys really know how to test software. They spend all their time writing software to test software, so you expect that testing to be. So given that, one question we have, which is quite interesting to us, is how much redundancy does an actually learn from tests? How much is it the case that there is always going to be a certain amount of redundancy, and how much redundancy comes from book over time, or from different tests, or perhaps code not written in a way that makes it easier. So we had to choose some kind of way of measuring redundancy. In this case, we have a range of metrics to look at, and we chose branch coverage. So here's my funny example, because I'm not a huge Java fan. And if we want to get branch coverage here, A is 1, B is 0, and we put in this branch of the if statement. And if we put in B is 2, we cover this branch. If you're a Jupyter practitioner, you might recognize this kind of function. If we take away the second part, and to get branch coverage, we'll still need the second division here, because we need to take a branch that doesn't satisfy this test. So that's the difference between branch coverage and statement coverage, where you wouldn't need that estimate. Okay. So our search objectives was the bi-objective problem, wall time based on the test suite, just running it and using a very simple Linux utility to measure wall time, and then branch coverage symbolized by this next. So there were two things we were thinking about, just as experienced software developers. I've worked in the industry before, and to me, regression testing kind of fits into two modes. The first is the kind of regression testing you do when you change the system, you actually don't want to cause any problems with the prediction system. And the second is something that's more informal, which is when you're changing code, you want to make sure you're not breaking things straight away. So you might want to restart the thing like that, compile. But the problem with that, of course, is the testing is really quickly. So we were interested in these two different applications of regression testing, which might have different characteristics when it comes to minimization. So here, we might be prepared to invest a lot of time in order to save time and deploying a lot of systems. In this case, we might want to frequently test. So this might need updating quite rapidly. We applied a GA to the form of test case memorization and used a simple representation like this, truly simple. A binary string. Well, actually, it occurred to me that it isn't a binary string. It's very weird because when you think about GA, you'll say binary strings, but this was in Java, so it was probably a Boolean string of booleans, which is interesting because I was building like this. But each entry in Java is a test in mode. It's a straightforward subset selection. This went on a long way to the right. This was the system, this is how it looked. So either there was a project, in this case, Pluto, with some coding in the tests. We used the MLEA framework, and we used the NSDA2 algorithm for the parameter optimization. And the fitness function was performed by using the global data in collaboration with the JCode project. So the gradable tool is an industrial strength data we've tested already and achieved a lot of projects. It's very, very modern, has everything you expect with a data tool. And the nice thing about JCode is it takes care of all the implementation. So it really, really nice reports and and the end result is ideally a set of global build files. So actually, there's a little bit of a package going on here as well. But generally, a set of global build files which will run different subsets of the depending on what the trade is. So this is the kind of thing we're looking at in terms of statistics. So this is the HTML output humans, can tell us how well our test coverage is going, what kind of instructions are missed, etc. This can go out to a data. It also produces things like this, which are profiles of lines that have been executed, the lines that have been missed, and your unit tests. Essentially, this data is also out there CSV and we use that to use our data. So in this work, there's a lot of testing in return, because it's written by testers, so you expect that. And we actually selected just a subset of the tests. One, because of the limitation in the system that we built, but also just because of the so we chose these packages, highlighted here in the blue, and 420 individual tests in total. I think we're over 1,000. And we ran a very simple experiment. Okay, so we set this up and we literally running it for 5 hours was people could do this overnight. Having said that, the results actually came earlier in 5 hours. We tried to tune the algorithm, which is the defaults, because this is a unique testing. We wanted to keep it as simple as possible. And we also could start this up by actually seeing the stats. And we didn't see downsides for doing that, but we could see that much less. So these are the results we got. The Pluto report, which is quite nice. Here we have the original testing, and then on the y-axis, bringing down runtime percentage, so it's 40% at the bottom. On the x-axis, a reduction in branch coverage. So that here we have 8% reduction in branch coverage. So a couple of observations. First of all, we can get a really steep drop in runtime without sacrificing much coverage. Secondly, the branch coverage loss is only 8%, even though we're finding the best savings we can, which is pretty small. And the savings in runtime overall are 40% rather than 8%. Thinking about branch coverage now, branch coverage might not be what you're interested in. You might be more interested in the fault finding capability, as we've heard already at this workshop. But at the symposium. But in our case, we were most interested in branch coverage. It seems that the evidence is mixed in the literature over whether that's a good idea or not. I'm not an expert, so we ran ahead with it just to see what kind of evidence we as well. And we looked at, why is there so much redundancy? How do we make these time savings? Well, the answer is, if you look here, we have a number of times each one is executed in a given file. So this is for one particular class. And you can see it here that a lot of lines in the file are executed a lot of time. So that kind of makes me think there's a lot of redundancy in the way our tests are constantly executing the same amount of code. And these tests are well written, because they're written by research developers. So why is that code executed so much? Is it because it's integral to setup? So you have to execute that code in order to apply the next test and the next test? Or is it because unit testing is limited in some way? It requires a lot of repetitive work. Or the third option, is it because the code itself is not written in a way to facilitate testing? For example, if you go to like a code editor, it will tell you to keep your methods really small and self-contained. And that really supports unit testing and we can use things to see. But I'm going to assume that these guys are really competent. And this kind of makes me feel that perhaps straightforward unit testing is not the best way to do that. Maybe we can test multiple things at once rather than continue re-executing the same code. But that's how we reduce the execution time by dropping the number of times down to the executed. In another example, you can see here, in the bottom right, we've actually lost the figures. So that's where we need to get into trade-offs. And I think as a developer in the industry, that would have worried me more. Executing things fewer times worried me a lot less than just not. And there's a good chance that this might be an edge case. It's not executed many times, and perhaps someone put that in there. The skill compared to the phrase. So, in conclusion, that we saw a 50% reduction in warp-up time while retaining 96% of the branch coverage of the test we looked at, sample of user. The test we I'm assuming is a high quality, by people expert in testing, actually contains a lot of redundancy in terms of benefit. That's quite interesting. And particularly from a point of view, an experiential point of view, applying search-based software testing here to Gradle-based projects, I think was pretty straightforward. Like I say, within a few hours, we have some results. I'm just going to make one more point, which is a general point about filters and automation. So in this case, it was really straightforward to apply search because it was, the project was organized very well in terms of the way the J units were written, the way they were organized, and the use of filter. So that made our job very easy because we could just hook into Gradle and we could use the Gradle system, for example, to measure testing. The entire Android ecosystem uses Gradle. So there are already many applications out there which use Gradle, which is interesting because it means perhaps this can be completely generic. We did discuss writing a generic code. We didn't do that because we're hackers and we like to save time. But that could be done in theory. But I think this is an instance of a greater trend we're seeing now. If you look on open source projects, and even in large organizations, there's a lot of automation going on. So there are tools like Jenkins and Travis, continuous integration. It's also continuous deployment. And you literally see thousands of plugins, things like Jenkins, where people are automating large parts of software tasks which used to be really domain specific, but they're plugging them into generic systems. And I think that's an opportunity for SSBSE generally, right? Because it means we can go in and mess around with stuff in a generic way and do large scale studies. So we should be able to develop tools and test them over very large numbers of projects, from GitHub, for example, and make stuff which is directly applicable to open source projects without having to change too much, removing some of the hard work. And I think perhaps in SBSE especially, because it's such an established field, it feels like the granddaddy of SBSE. Perhaps at the beginning, it's just so much harder to do that, and there are new opportunities even for old and established techniques. Okay, so that's everything I have to say. It's 50 minutes or 50 minutes-ish. I'll take any questions now.
Are there any questions for our second speaker? Right, and you can see how
Converged, what in that sense?
example, you can use the reading outside of the game.
So the question is, did we do anything to check whether we reached the actual creature from the web browser approximation? Other than doing several runs, no. So comparing runs, we tweaked a few things, and then had to rerun to make sure we get the same or comparable results. So the answer is no. But that would be a very sensible thing to do.
Are there additional questions? I do have one question. You mentioned that you used the Coco for collecting the coverage information. I'm stretching my memory a little bit, but does the Coco collect coverage on a per test suite basis or on a per test case basis? And how did that change the way that you implemented your search?
Right, so you're on my memory as well. I think we looked at both in our pattern. So it isn't based on methods, I think, but we also looked at, we did two types of experiment. One where we looked at classes and one where we looked at methods. Okay. Test methods. And here we looked at test methods to what kind of way. In terms of, we had to do a little bit to get that to work. So it's a bit of Java. And we could go around that nice. That's most petitions which is off the shelf, changing very good. That's what we use in my estimate. That's about it. But I think that could be a perfect reasonable hypothesis to make based on any result. Yeah. I'm sorry, I didn't repeat your question. So the question was, these guys know what they're doing. There's a lot of redundancy when it comes to branch coverage. Does that mean that branch coverage is bad as a metric for trying to speak on that? Yeah. Yes, it's,
Just wondering.
discovered. And these guys do know what they're doing. So branch coverage, reducing redundancy of the branch coverage may result in a loss of fault finding ability. Yeah, I kind of agree with that. In the industry, it's standard practice where if something goes wrong, you make sure it can't go wrong again, and one way to do that is to create a test. So perhaps you need to be a little bit smarter about the way you guide them and analyze things.
Is there a final question for our speaker? Okay, thank you very much.
Thank you.
To welcome our third speaker. Tryon is going to be telling us more about code evaluation, and in particular, how he conducted a replication study. Let's welcome him for this presentation today.
So thank you. Today, okay. Yeah, as I was introduced, so I'm going to talk about clone fiction, which is a bit off from the topic of search base, but is the way that you can use search base to tune the clone detectors And we based on a study, a paper that has been introduced in, it's a framework called EVA clone, which you can use to tune the clone detectors to maximize the agreement. And we're conducting a replication study here by applying it to mosquito with different settings to see how it works in a new environment. And this is the work that I have done with friends at UCL. So Mathis, Paishao, Sonal, Atam, Sahid Bukhari are PhD student at UCL. Yang Sprinter is my supervisor, and John Drake is at Primary. So I'd like to tell you a bit more about code clones. So code clones is a piece of code that developers copy to another location and make some modifications to fit with the new environment. And this process can repeat many times. It depends on whether it's a good written code that you want to reuse, or developers are just lazy and just copy their own code. So with these similar fragments of code, you need an approach or a tool to locate them, because sometimes you have bugs in the original code, and then you want to look for the clones to fix those bugs. It also helps in the study of how these clones affect the quality of the software, and there has been a lot of work on this area. So with the clones, we have various approaches that you can use to locate clones. And the first one is you can just compare strings based on textual similarity of the code. And by doing that, we pick one tool for this study. It's called Schemion. You can also turn the source code into tokens. So you make one more abstraction from the source code and compare the source code based on this token at this token level. We have one tool which uses token-based clone detection technique. It's called CC Finder in so we call it it's called CC Finder. And there's also some tools which use hybrid techniques between two approaches. And we also have a tool called Nightcat, which is a combination of token-based and string-based clone detection. And the last one is the tool that hasn't been used in the original paper before. It's clone detector that's based on structural similarity of the source code. So a tool called Descartes here is a clone detection tool that turns your source code into abstract syntax tree and do similarity detection at that level. All right. So we always have this problem of Oracle import clones, which means when you apply a clone detector to a system, and then you get clones. Or you have to manually check all of them to make sure that all of them are clones. So mostly people just rely on what the clone detector reports as clones. And there's a paper that come up with this idea of agreement. Just one tool that you're going to rely on. You can have the agreement of more than one tool. So let's say you have this pair of clones, and you're not sure whether they are real clone or not. So you can have, in real life, you can ask your friends, right? So you have 6 friends, for example, and you ask them. So 4 of them say they're clones. So you have more confidence that this pair is going to be real clone. So based on this idea, so we replace the people with the clone detectors, and you can have so you can have more than one clone detection tool, and you find agreement among them. So that seems to be a good idea. The main problem here is when you have just one tool, configuration of the tool parameter is very difficult already, because it has a lot of effects to the tool behaviors and the result that you get from the clone detector. When you combine them, so you get even more complex configuration that you have to go through. So This is the paper that our work is based on. So it's a framework called EVA clone. It's a work by Wang Tiantian and people from Press at UCL. So the idea is you have 6 clone detectors. It can be any number of clone detectors, but in this paper it's 6. And using that 6 clone detectors, you try to use genetic algorithm to tune the parameters in the way that you maximize the agreement of the two based on the clone reports. So you want to tune the two to report the same clones as much as possible. They apply these 6 tools on 8 software projects, which without the tools, it can take 15 years to run. So this code detection is expensive, and if you want to repeat it many, many times, it takes a lot of time. So that's why genetic algorithm is needed here. So the idea of this optimization of the agreement is when you have multiple clone detectors, if you use the default configurations, let's say I have CC Finder, Descartes, NiCat, and Simian here. The default configurations might give you this. So let's say this blue area is the clones. The yellow area are the region that the tool report as clone. So the agreement in this case is, so based on the number of tools, the pink region is the area that all the two agree. And that's what we want to maximize. So you want to relax or changing the configurations in the way that you get this maximum agreement between the two. That's the main idea of the EVA clone framework. So it turns out that using EVA clone framework compared to the default configurations, this graph shows you the percent of improvement from the default configurations in terms of agreement of the tools that you're gonna get. EVA clones always give you better agreement among 6 tools. And it tends to favor recall over precision, which means you get more clones, but you will miss fewer of them compared to the default configuration. So motivated by this paper, I made so we made this replication study by choosing tweaking the tool set a bit. So instead of having just only string-based and token-based clone detectors, I added the structural clone detectors, which is Descartes in this case, has not been used before in the original paper. And we applied it to Mockito. So by doing this, we also improved the performance of the EVA clone by introducing caching infrastructure. So instead of you just keep running the tool, even you use the same configuration over and over again, you just save the clone report of each particular configuration in our cache. And when you run the same tool with the same configurations again, you just reuse the clone report. And we found that using this kind of caching can speed up the framework by a lot. So the fitness calculation is, as I told you, is based on the agreement of the two. So I'm going to talk about it a little bit more here. So this is the fitness function that's proposed in the original paper. So the main idea is if any lie are reported by more clones, you give them more weight. So the lies that are reported by 4 clones, 4 clone detectors too, gonna have higher weight than the lie that are reported by only single tool. So based on this fitness function, we run the genetic algorithm using the chromosome of 25 parameters that we get from these 4 tools. And if you do exhaustive search on this search space, you're going to get about 2 trillion possible combinations. So that's why we also do the search technique here. And all the configurations here use the configurations that are already used in the original paper. Okay. As I told you before, we applied it to Mockito. And instead of applying to just one release, we apply the framework to to 14 major releases, starting from 0.9 up to 2.0.44. That span over 8 years of Mockito framework. So at the very start, we interested in whether this kind of clones will be how many of the clones we're gonna file in Mockito, because we expect that in test framework you might find a lot of duplicated code, right? And that's one of the main motivations that we choose Mockito. And with this increasing size of Mockito from 5,000 line of code into 25,000 line of code, we expect to see something interesting. And we hope it's going to be challenging for the framework. So the first research question that we want to answer is, with the same framework applied to Mockito, is the framework still outperform the default configurations? And we found that if you use EVA clone to tune the tool across all 14 releases, you get better agreement from the 4 tools. So for each particular release, we run it 20 times. And even with the lowest agreement that you get, which is the X symbol here, still better than the default configurations. The second one is, we would like to see if you get one optimal configuration from one release, can you just use it and apply to another release, and you don't have to run this kind of optimization again? It turns out to be not really, because what you found from here is the optimized parameter that you get from EVA clone keep changing over releases. There are some areas that you get a very similar settings, but there's no single setting that's going to work for all 14 releases. And that's true for all the 4 clone detectors that we have here. Okay. So the last question is, this is something that has not been done in the original paper as well, and reading what we found is very interesting. So we look into the number of clones that are reported by the framework. And what we found is the pink bars are the ones that are reported by default configurations, which is pretty stable over 14 releases. The black region is the one that reports by 4 tools. And yeah, going down by 3 2, 2 2, and 1 2. And when we apply EVA clones in this region in release 0.9 and 1.9 up to 2.0.44, you get more clones. But that's conformed to the original paper that says it tends to prefer recall over precision. So you get more clones. However, this region is interesting, because you can see that EVA clone gives you a fewer clones than the default configuration, but in a way that you still get the maximum agreement anyway. So we found that what happens is, instead of maximizing by relaxing the configurations, it can also go this way, in a way that you get fewer clones, but you still get the maximum agreement anyway. And that's what happened here. I think the main message for this paper is the fitness function in EVA clone is still flaky, and it still has a room for improvement. So because maybe it's just single objective, and we might have to think about multi-objective here to make it more stable, such as you might include frequency of the clone fragment, how many times it has been copied, or choose either to go into the direction of precision or recall, but not both of them in the way that I'm expected. And or you might, instead of counting just number of lines, you can look into each particular location of clones and find the agreement and that in each location. But it's still work on progress, and we're still working on it. I'm really happy if you have any suggestions to improve the fitness function, and we think it's really interesting to work on this. So To summarize, I have done a replication study of your clone framework. We found that it gives you better agreement than the default configurations. But we don't find any stable configurations over releases. And the fitness function still needs improvement. So that's it. I'm open to questions now. Thanks.
Who would like to begin with the first question for our speaker? Yes, please go ahead.
Okay. So the question is, the optimal configurations might be subjective to each particular program. And yeah, I agree with you. And but in this case, we use only just one program, which is multiple. And you can see that just from one release to another release, we have checked for the percentage of change in the source code. And it turns out that it was not a big change introduced into the system. So so in this case, I don't think that's the case about the difference in the software. It's mostly about the fitness function. But I agree with you that you apply to different software or different systems, then you get different optimal configurations.
Your results get by the manual all day. Different data sets, different learners, different configurations. So now all analytics
Thanks.
Are there any additional questions?
Suggestions? We need the one.
I did have one question. So for your second diagram that's on the right at the top, you said the results really vary across releases and
Yeah.
Can you talk a little bit more about how these might be specialized, the results are specialized in the releases? Like you said, they're all very small and then changes. What if there were big changes? What would your results look like in that?
There's a big changes at this release. So between 1.6 and 1.7, big refactoring has happened in multiple, and we think that with that change, the optimal configuration is totally changed. So yeah, it has a lot of effect on optimal configuration, and we think that if you want to do this kind of parameter tuning, you have to repeat this process of tuning every time that you have the new system.
Okay, let's thank our speaker with a round of applause.
Thank you.
I think we've come to our lunchtime session. Thank you all for being here today.
Yes, so for lunch it will be in the room next to the yesterday lunchroom, so on the top floor as well. So we'll be ready in 2 minutes so you can start doing it. Thank you. So we came back at 2 p.m. with the next session. Yes, it's a good luck. So these are the room. Yes, yes. Because I have 2 people working on it. It doesn't mean but the last